This video is brought to you by mywayteaching.com.
In this part, let us solve one more simple problem. Example 5. A pipe 30 centimeter long is open at both ends. Which harmonic mode of the pipe resonates a 1.1 kilohertz source? Will resonance with the same source be observed if one end of the pipe is closed? So take the speed of sound in air as 330 meter per second. Okay, the question is whether the resonance with the same source is observed if one of the end of the pipe is closed. What will be that resonance when it happens if one of the end is closed? Let us find the solution for this. The first harmonic frequency is given by V1 is equal to V by lambda 1, that is equal to V by 2L for open pipe, isn't it? Where L is the length of the pipe, the frequency of its nth harmonic is given by Vn. We studied this. That is given by N by 2L, where N varies from 1 to 3 and it continues. The first few modes of an open pipe we can see in these figures: the fundamental, third, fifth, 7th, 9th, 11th, and in the question they have given the length L is equal to 30 centimeter and B is equal to 330 meter per second. In that case, Vn is equal to N V by 2L, that is 0.6 meter, which gives 550 N per second. A source frequency of 1.1 kilohertz will resonate at V2, that is at second harmonic. This is the first case. Now, as they have asked in the question, if one of the end is closed, in that case, we'll get an equation for one end closed, that is V by 4L, pipe closed at one end. And only the odd numbered harmonics are present. That is V3 is equal to 3V by 4L, V5 that is equal to 5V by 4L, and so on, isn't it? And in the question for L is equal to 30 centimeter and V is equal to 330 meter per second, the fundamental frequency of the pipe closed at one end is given by 275 Hz, and this corresponds to the source frequency. The source frequency corresponds to its fourth harmonic. Since that is not possible in this particular case because it only have odd harmonics, no resonance will be observed with the source. The moment one end is closed, we can't observe that resonance in this in this particular case. Resonance is observed only in case of if both the ends are open. Okay, not here. Now let us study about beats. Beats is an interesting phenomenon arising from interference of waves, which means when two harmonic sound waves of close frequencies are heard at the same time, we hear a sound of similar frequency. But we hear something else also, isn't it? We hear that audibly distinct waxing and waning of the intensity of the sound with a frequency equal to the difference in the two close frequencies. Even artists they use this phenomenon while tuning their instruments with each other. They go on tuning until their sensitive ears do not detect any beats. We do it, right? So, to see this mathematically, let us consider two harmonic sound waves of nearly equal angular frequency omega 1 and omega 2 and fix the location to be at x is equal to 0 with the suitable choice of phase. So, let us take phase as pi by 2 and assuming equal amplitudes, it gives S1 is equal to A cos omega 1 t, S2 is equal to A cos omega 2 into t. So here we are referring to the longitudinal waves. We have replaced the symbol y by s. We are not referring to the transverse displacement. So let omega 1 greater of the two frequencies. Okay, omega 1 is greater than omega 2. Then the resultant displacement by the principle of superposition, we can write S is equal to S1 plus S2, that is equal to A cos omega 1 into t plus cos omega 2 into t, isn't it? And using the familiar trigonometric identity for cos A plus cos B, we can write so from the principle of trigonometric identity, we can write cos A plus cos B is equal to 2A cos. For this particular case, we can write two a cos W1 minus W2 into T by 2 into cos W1 plus W2 by 2. So which may be written as S is equal to 2A cos omega t if omega 1 minus omega 2 is less than omega 1, comma omega 2, and if omega A is very much greater than omega B, then we can write omega B as omega 1 minus omega 2 by 2 and omega A as omega 1 plus omega 2 by A. So now if you assume the omega 1 is less than omega 1, which means omega A is greater than omega B. So the resultant wave is oscillating with the average angular frequency omega A. However, its amplitude is not constant in time, unlike a pure harmonic wave. The amplitude is the largest when the term cos omega B into t take its limit from plus 1 to minus 1. In other words, the intensity of the resultant wave waxes and wanes with a frequency which is nothing but 2 omega B is equal to omega 1 minus omega 2, since omega is equal to 2 pi V. So we can write the beat frequency as V1 minus V2. Okay. This figure, it illustrates the phenomenon of beats for two harmonic waves of frequencies 11 Hz and 9 Hz. The amplitude of the resultant wave beats at a frequency of 2 Hz. You can see here. The resultant wave is here, and at 11 Hz and at 2 Hz the waves are oscillating. Superposition of two harmonic waves, one of frequency 11 Hz, that is A, and one of frequency 9 Hz, it gives rise to a beats of frequency 2 Hz. Okay. Now let us see one example. Two sitar strings A and B playing the note dha are slightly out of tune and produce beats of frequency 5 Hz. The tension of the string B is slightly increased and the beat frequency is found to decrease to 3 Hz. What is the original frequency of B if the frequency of A is 427 Hz? That is the question. See, increase in the tension of the string, it increases frequency also. Okay. If the original frequency of B, will take it as VB, okay, were greater than that of A, then further increase in VB should have resulted in an increase in beat frequency. But here the beat frequency is not increasing, but here it is decreasing, as they have given in the question, isn't it? If VB is greater than VA, if that was the case, if you assume, then in that case the beat frequency would have increased. but that is not happening. Instead, if you increase VB, the beat frequency is decreasing. So this clearly shows that this frequency VB is less than frequency that is of A. Okay. Since they have given the beat frequency, we can write it as VA minus VB is 5 Hertz. And in the question, they have given the frequency of string A as 427 Hertz. If you substitute in the equation of beat frequency, we get VB, which is equal to 422 Hertz. So this is the frequency of string B. Okay.